So before we talk about using generalized Fourier series expansion to represent continuous function fx, now we show another way to solve the BVP use generalized Fourier series. Okay, so BVP solution using generalized Fourier series. And we will show an example, very familiar one, where the y double prime plus 4y equals to 1 with the boundary conditions y0 equals to 0, yl equals to 0. Okay, and you can solve this BVP, the homogeneous part, which is y double prime plus 4y equals to 0. So the homogeneous part y double prime plus 4y equals to 0. The particular part is y double prime plus 4y equals to 1 using undetermined coefficient. The homogeneous part is basically an eigenvalue eigenvector problem. After you solving the homogeneous solution, you can guess what is the particular solution look like using undetermined coefficient. Then after you solve the general solution, which include the homogeneous part and the particular part, you can put the boundary conditions in, trying to figure out what is the unique solution. Okay, so the exact solution, we won't solve this in class, but you can try to solve by yourself, and the printed out note has the exact solution with the detailed math there. The exact solution using the previous step you can get is yx equals to minus 1 over 4 cosine 2x plus cosine 2l minus 1 for sine 2l sine 2x plus 1 over 4. So this is the exact solution for the BVP showing here. Then we are trying to use generalized Fourier series to solve this BVTB solutions. How we do that? So let's see, using Fourier series. And we know that from y double prime plus 4y equals to 0, that is basically our Stern-Duval problem set, which is the minus y double prime equals to 4y. We solved this before. We got our eigenvectors yn equals to sine n pi x over l. My lambda n is n squared pi squared over l squared. So those are already solved. We also know that fx equals to 1, which is the right side of my BVP, the ODE. The fx equals to 1 equals 2. This can be represented by the generalized Fourier series with a linear combination of all the orthogonal basis set, which is the sine function here. So n from 1 to infinity, bn sine n pi x over l. And after we solve the bn part, we can get that should be 4 over pi sum from n from 1 to infinity sine n pi x over l divided by n, where n is all the odd number, n from 1, 3, 5 until infinity, all the odd number. Okay. If so, we already know the homogeneous part, the continuous function can be represented by the orthogonal basis, which is the eigenvectors. We also well know that the x can be represented by from n equals to 1 to infinity, bn sine n pi x over L. Then since we know this Yx function is a linear combination of all the basis sites, then we will know what is the Yx prime and Yx double prime, right? So Yx prime is basically the derivative of this Yx, which will be the sum from n equals to 1 to infinity bn times n pi over L cosine n pi x over L. The Yx double prime, which is the derivative of Yx prime. So that is the sum from n equals to 1 to infinity bn n square pi square over L square sine n pi x over L. Then what we can do later is we can substitute Yx prime, Yx double prime with the generalized Fourier series format into our original ODE, which is y double prime plus 4y plus equals to 1 to figure out what is our coefficient Bn here, okay? So the next step is we substitute y prime, y double prime into the original ODE, which is y double prime plus 4y equals to 1, okay? And after doing that, we can figure out what is our Bn. So let's try to solve this problem. So y double prime plus 4y equals to 1, where my y double prime equals to the sum from n equals to 1 to infinity bn n square pi square over L square sine n pi x over L. Y equals to the sum from n equals to 1 to infinity bn sine n pi x over L. So we can get y double prime, the sum, sorry, this is minus sign here, so minus bn n from 1 to infinity bn n square pi square over L square sine n pi x over L plus 4 times sum from n equals to 1 to infinity bn sine n pi x over L. That should be equals to 1, where this 1 can be also represented by the generalized Fourier series, which is 4 over pi sum from n equals to 1 to infinity sine n pi x over L divided by n. Then we can just put all the coefficients together for the sine n pi x over L, right? So what we can get is 4 minus n square pi square over L square times bn, the sum from n equals to 1 to infinity sine n pi x over L will be equals to the sum from n equals to 1 to infinity 4 over pi sine n pi x over L divided by n. Okay, and since this part are the same, the sine n pi x over L is the same, the sum part is the same, that means the coefficients needs to be same so that the left side will be equal to the right side. Then we get 4 minus n square pi square over L square bn will be equals to 4 over n pi, okay? Then after that, we can get our bn will be 4 over n pi, 4 over pi times 1 over n divided by 4 minus n square pi square over L square. And after you get the bn, you know that the Yx as the initial format is a generalized Fourier series from n equals to 1 to infinity bn sine n pi x over L. so that the Bn is here. You can know what is the final solution for u of x, which will be 4 over pi, sum from n equals to 1 to infinity, 1 over n divided by 4 minus n squared pi squared over L squared sine n pi x over L, where the n is only the odd number, 1, 3, 5, until 2, infinity. So this is how you can write the boundary value solutions using generalized Fourier series. Okay.